Hello everyone, my name is Mihai, some of you already know me, and I'm gonna be the host of this event. During the presentation, please keep your microphones muted and use the chatbot for questions. I will make sure we answer all the questions you have at the end of each talk. We will have a Q&A session then. And I remind you that all our sessions are recorded, and after we finish the event, we will upload the recording on YouTube. We'll publish it there along with the slides. So you will have the possibility to get the slides and rewatch the recording if needed. That being said, let me welcome Paul, our first speaker today.
Hey, everybody. I'm very happy to be here. Well, here being my house in the basement. I would rather be in Amsterdam and going to L&B's after this, but it is what it is. So what I'm going to talk about today, and let me make sure that this, oh, wait a minute. Can you, oh, that's odd. You seeing my whole screen, or are you seeing just the?
We only see the slides, but not the whole screen, not the full screen.
You do see the slides though, because it just changed my desktop. Okay.
Yeah.
How about now?
Looks better now. Yeah.
Okay. Full screen?
Full screen.
Okay, great. So let me introduce myself. My name is Paul Venezia. I'm the chief architect for the DTS Connected Radio product, service, API, and I'm going to show you a little bit about what we do in the first few slides to give you some context. But what I'm going to talk about today is API authentication and scalability using OpenResty and Lua in Kubernetes. So let's just jump right in because it's interesting stuff to me anyway. So some background on DTS Connected Radio and what we do. It's a global API. We deliver metadata to cars, to automotive clients all over the world. We need to support all major geographic regions in the world where you would find cars. So we need to be pretty spread out. We also need to scale substantially. We also need to be able to provide this service for a long period of time. Once something's in a car, it tends to stay in a car. It's not like a mobile client that you can, do OTA updates frequently. One of the things that we do is terrestrial radio broadcast, where we distribute radio station names and logos, streaming URLs, currently playing information like the song, a picture of the artist, that type of thing, as metadata enrichment to broadcast radio. So you tune your radio to hear the audio, but the metadata comes through our service. We also have a podcast catalog, an internet streaming catalog. We have events information. So if you're listening to a jazz station, for instance, you could hit a button and it'll show you all the jazz concerts that might be upcoming in your area. We also do automatic content recognition, which is where you can feed us a fingerprint of audio, and we'll match that to a song name and an artist and provide information on that artist or that song, album covers, that type of thing. And we provide general music artist and song information catalogs. So I'll give you a quick, tiny little demo just so you have some context. This is a web demo of our service. It hits our API just like a car would. So you can see like we're in a car here. This is what your radio looks like on connected radio. So if you were in London, you would have all of the radio stations that are receivable in London, and you'd be able to see what's playing on them right now. So I don't even know what that is. Do I Want to Know by the Arctic Monkeys is on BBC Radio 1. And here's the album cover. There's the Arctic Monkeys, the name. You can thumbs up, thumbs down. I can look for events in the area. I can stream it. This means the stream is playing right now that I'll mute. So this data comes directly to us from the BBC and other broadcasters. But what we provide is a service like this globally. So there's a lot of real-time data that needs to be delivered. There's a lot of obviously client lookups, queries going on in the background to provide this type of service. So how do we do it? we are, or what is it? So we have as I said, a global API that needs to run and be reliable all over the world in the major metropolitan areas. Customers are automotive. We're built out on GCP, which was a choice because of the extensive Kubernetes tooling predominantly and cost. So we chose GCP a while ago over the alternatives. Heavy use of Kubernetes and Helm. Most of our endpoints are written in Python or Golang, depending on what they're doing. We use AMQP extensively. We have found AMQP and RabbitMQ to be very, very well adapted to our purposes. We use Postgres, Redis, Elasticsearch, the usual suspects. But we also use OpenResty, which isn't a usual suspect, and that's going to be what we're going to talk about today, specifically around authentication. So our design requirements for delivery are similar to most APIs. I mean, you never see an API that has it doesn't need to be that fast. No, we want it to be as fast as possible, highly available, scalable. We also want to be as efficient as possible. We don't want to just throw money and resources at this problem. I don't want to be managing cloud infrastructure spend that just keeps growing exponentially. We wanted to make this as tight as possible within our requirements and as efficient as possible. And no multi-tier delivery, if at all possible, meaning that we don't want to do a database lookup to a database tier to respond to a client query if we don't absolutely have to. And for our heaviest endpoints, we don't. We also wanted to have vulnerability protection and, for spurious requests, DDoS. Some of that we can rely on the cloud provider for, but we also wanted to have our own protection in front of this. And all authentication data should be managed on the fly, meaning that we shouldn't have to, for certain things that do authenticate each request right at the edge, at the very edge. It shouldn't require a pod restart. There shouldn't be anything, even if it's not doing any lookups anywhere else, it should automatically be able to update the authentication tables. Has to start fast. When you're scaling, we want to scale as fast as possible. Able to handle multiple different authentication methods and back-end APIs. I don't want to have to create one of these sidecars for every endpoint. I don't want to have to create one for every even API. I want to have the ability to distribute these things, to write this once and consolidate all of that code, make it tight and solid, and use it everywhere. So we want a single, consistent configuration and deployment across all endpoints with an agnostic configuration, no specific paths. And this is where some of our tooling comes in, like Helm, to create these configs. But predominantly, the idea is to do this right, do it once, and use it everywhere. And also, if at all possible, the back-end services do no authentication work of their own, meaning that when they are queried, the client queries for data saying, what's playing on this radio station, the back-end service that actually sends that data to the client does no authentication work. It's all handled absolutely at the edge. So the tools required to make this happen and what we built is Kubernetes and Google Cloud, the GKE service. We use a global multi-cluster ingress that feeds Anycast to all of our endpoints, no matter where they happen to be. It's going to find the closest one. Handles the TLS offloading for us, and we're going to use the sidecars on the Kubernetes services to run the OpenResty service itself, the process. And we're using OpenResty with Lua and Lua just in time, which is in OpenResty, and I'll explain a little more on that in a minute. We do use Redis caching in some places for delivery if we can. A lot of our queries are not really cacheable, so they need to be handled one by one. And we have the option of using Redis to actually be our authentication store, straight out of OpenResty or Nginx. So this is what we use to build the auth service and the front end that we have. So let's talk a bit about OpenResty. OpenResty is, as this is what they say on their website, a full-fledged web platform, integrates our enhanced version of Nginx Core, an enhanced Lua JIT, a lot of Lua libraries that are optimized, third-party Nginx modules and dependencies, and it's basically designed to be a clearinghouse for fitting as much in the front end as you can without relying on back-end services written in anything else to deliver data to a client. This is very much suited for APIs specifically, but you can use it with anything. So Nginx has non-blocking I/O, and OpenResty with Lua allows you to do SQL queries, hit Memcached, hit Redis directly from the Nginx service itself using OpenResty. It's not a fork. It uses Nginx, and they contribute patches back to Nginx Core that are usually accepted, a lot of optimizations. But the really important part for the authentication here is the incorporation of the Lua JIT engine, which is embedded in OpenResty. Now, you could build Nginx with Lua, and there's a whole bunch of projects out there that do things like that. I found OpenResty to be the most complete, and they optimize Lua itself and the Lua JIT engine to be as performant as possible in the context of using Nginx as your front end. So, what is Lua? What is Lua JIT? It's a just-in-time compiler for Lua, and Lua itself is a very lightweight programming language. It's syntactically interesting at times. It was developed in Rio, Brazil, still maintained there. It's designed to be very fast. It does not have a lot of the normal comfortable conventions that you might find in languages such as Python or even Go. But that's because it sacrifices some of that ease of development for speed and scalability. And so what you'll get is only the things that you need. And there's garbage collection. There's the bigger parts. But it's heavily used in games like it's Angry Birds and World of Warcraft use Lua JIT. It's used in appliances. It's used in Photoshop Lightroom, industrial applications. It's very embeddable, very small memory footprint, high performance. That's the optimization. So this is one of the key things that makes this implementation, the front end auth implementation tick, is that we can write it in Lua and use Nginx to do it. So here's the concept of handling authentication in this manner. Clients would connect through a normal ingress into an OpenResty sidecar running in Kubernetes with the other service in the pod being the actual endpoint that is supposed to be delivering the content to the client. So the Lua code handles all the authentication, and the request is passed to the appropriate backend only if the authentication is satisfied. We have the request logged, and any issues with authentication, such as updating authentication or something happening that would prevent proper operation, that should be logged. And then we gather metrics on performance. So all of this happens ahead of the actual API endpoint. This is all done in Nginx or in OpenResty with Lua. So this is one of the ways that we get the high performance and the highly scalable scenario that we have now. So it looks something like this. You have your API client that flows in. Let's see. Look at that. So your API client hits our ingress just like normal, and the ingress delivers the request to a delivery pod that's in a sidecar. Now this sidecar has authentication tables either present within shared memory within the sidecar, or it has a way to query an authentication backend to pass credentials or a token or whatever, and then it can cache it. There's a number of different ways that I will go through in a moment on how you can use different methods to actually do the authentication check. Hang on. So these auth updates are either live as a request comes in, or they're cached in the sidecar itself. So then the auth check happens within the OpenResty sidecar, and then the query is passed to the delivery backend in the same pod. So here's your ingress coming into, say, port 8000, and then if it passes the check, it would get kicked to the local pod 8001. And then that's where the actual API service is running. So what are the design considerations about making that actually work? How do we handle the auth? How do we handle the tables? What are our options? One of the methods that's easiest to discuss here, and to be frank, we're talking about authentication, so I'm not going to go into a lot of detail about how we perform auth. I'm going to showcase a few possible methods in a very kind of opaque manner, but you will definitely get the idea. The sidecars have to be self-sustaining, meaning once they're deployed, I don't want to have to restart them for any reason if I don't have to. If they have local auth tables, then a timer should fire within each sidecar that would check for updates, auth updates. And this could be, whatever tunable you want. It could be 5 minutes, it could be 20. Depends on really on how your authentication requirements are structured. If it's an API where every user has independent authentication that needs to be checked on every query, then you're going to have to do this a different way. But if you're authenticating devices in the field that have fixed IDs and things like that, then this becomes very interesting because it's very scalable for implementations like that. So we need to use shared memory within the pod, because when we pull an auth table into the pod, the OpenResty workers there can be a lot of different worker processes, and they all need to be able to reference a shared memory space to do their in-memory auth lookups. And any worker has to be able to initiate the table updates because of the nature of the worker structure within Nginx and OpenResty is that when you create timers, any worker may be the next up to actually get the timer fire and do whatever has been instructed in the Lua code. So that took a little finagling. And then we're talking about, in this case, shared memory authentication. So we create a shared memory space within the pod that we stuff all our authentication data into. So our auth tables are sourced from either Redis. We could query a Redis instance and get back a table, or compile one. We could use Kubernetes secrets. There are a number of different ways that we could retrieve. You could do a Postgres lookup. A number of different ways that we can get the auth into each pod. But we also want to make sure that we're protecting ourselves from possibly ourselves or possibly something unexpected from going on. So we need circuit breakers. If we have an auth table that contains 20,000 records and we do an update and that auth table only contains 5,000 records, we probably don't want to continue. We want to say, no, that update doesn't look right. I don't want to jeopardize proper operation. I'm going to reject the update. So you want to take care to do things like that, because these are not being pushed, they're being pulled. But you can override that circuit breaker. So if you do have to make a substantial change to the auth in a pod, you can override that circuit breaker and force that change through, but it has to be done manually. So in the context of shared memory authentication, these were some of the design considerations that we had. So in practice, it looks like this. The delivery pod starts, and it creates that shared memory space for the authentication tables. And then the shared memory is populated from wherever it comes from. So now you have your table built in memory. And then we have protections for bad data, large number of table changes. Is a table format consistent? Does it validate? Any number of tests that you want to write in here. You log it over here, and then every worker in that pod uses that shared memory space for authentication. When the timer fires, you go get the latest update of the tables, and then you rinse and repeat. So this is one way that we populate auth data in a way that is secure, and it's only stored in memory. If that pod goes away, it goes away. And we have various methods to ensure that no data is clear text or plain text on the wire. So here's an example in Nginx of how we would implement a Lua authentication backend. So this is, if you're familiar with Nginx, this is just a location block. We have some cores include here that we needed to implement. And then we have two authentication schemes, and they're bracketed here because they're, you call them whatever you want them to be. This is Redis, this is what a shared memory, whatever it is. So then we tell Nginx we don't need to send the request body to Lua, the Lua code, because we just need the headers. We're not, and if you did need the body, you could send the body. We don't, and this speeds up processing. And then we define access by Lua block, meaning that only if this passes does processing on this request continue. So then we set some options, which in this case are blank, or we could pull from somewhere else, and this would be passed to that, their parameters passed to that Lua script. And then we require the auth, which is the name of the file with whatever scheme, and this is actual Lua code, and we pass it the options. And then, if we get through this access block, then we proxy pass to the local pod on port 8000, which is where our actual service is running. So that is the actual API endpoint. So if auth fails, processing stops here. The 401 is issued to the client, and off we go. If the auth succeeds here, then this is passed to the back end, and everything works as normal. And this is, we create all of these with Helm templates, but I mean, obviously you could do this in a standard Nginx config. And then this is what the Lua code looks like for the shared memory API key. This is very simple. This is just, do we have an API key that exists in our shared memory that is set to enabled? So this is Lua code that says, we have a function that gets the XAPI key from the request headers. So we set a local variable to be the Nginx header, the HTTP XAPI key. So this will pull in the header from the request that is titled XAPI key. So if we have one, then we test to see if it's present. So we look at our shared memory to a table called internal API keys, and then we try to get it. If we get it, if this succeeds and enabled gets the string enabled, then we return authentication passed. That API key is accepted, we're good. If it doesn't, then we don't return, and we throw an exit with a 401 straight from the Lua code. So Nginx doesn't have to do anything else. It just exits with that 401. So in terms of actually testing API keys, this is incredibly fast. This is literally just, it's not even a Redis lookup over the wire. It's all in RAM within Nginx. And as you can see, you can get very more involved with this Lua code. You could have different states of those keys. You could this is where you could do expirations if that key is too many requests. I mean, there's a whole host of things that you can do here, all within the Lua code running in OpenResty before it even gets to an endpoint. So pretty simple example, but I think it tells the tale. So there are some extended design considerations that these are things that we have done, we didn't need, we may need, we thought about, and they may apply more broadly, so it's worth discussing here. You could do Redis auth. You could just have Redis sitting behind here doing handling the back end where you're just writing keys out as needed and having Lua do the front end and do the Redis query, and then even stuffing that into shared memory with expirations. You could use Redis to distribute the authentication table, so that timer just goes and hits a Redis key, as I mentioned before, and gets whatever auth it needs. You could use API auth. You could do a RESTful call to an authentication endpoint, passing the headers along, or the body, or whatever you want, and then making a decision at that point whether or not to authenticate the request or not. I mean, obviously that's going to be heavier. There's more going on there, but you now handle all of that again right in OpenResty and not in Python code or even Golang or the endpoint code itself. As I said, we use AMQP. It's a very extremely fast, efficient, and well thought out protocol. You could use it to publish the auth tables as well. There are AMQP libraries for Lua that allow you to bind to AMQP queues and routing keys, so you could just publish the table whenever you wanted to, and it would automatically be distributed to every OpenResty instance. You could use it for event emission, for metrics and logging. With the non-blocking I/O, you're just publishing on a key. You're not even doing a RESTful API call. You're not worrying about logging out, standard out. I mean, it's an option. It may not apply to everyone, but it's certainly a way to distribute events that could set off triggers in various places. There's a lot of options when using AMQP in this case. You could also use it to trigger actions like auth updates. You could trigger rereads. You could trigger anything through AMQP. It just provides a means of effectively RPC calls to the OpenResty service itself. In addition, you could take this out of the sidecar and create a standalone configuration of OpenResty that runs as everything in front of an API. If you're not using Kubernetes and you need an API gateway, you could build this with a reverse Nginx or OpenResty functioning as a reverse proxy, handling TLS termination, load balancing, and authentication all in the same service. So you could build out these API gateways that literally do everything for you. In addition, I don't have it listed here, but you can make some serious performance increases in a few different very judicious use cases with Varnish and VCL. You can even have VCL do various checks in front and cache auth to speed things up even further. The options are there. And as I said earlier, multiple authentication mechanisms and backends supported. So when we first designed and built this, we only had one in mind, but we've since extended it to everything. So this mechanism is so broadly applicable that it doesn't make sense to do multiple different methods and multiple different mechanisms. So let's take a look at some of how that works. So if you have multiple sources and backends, you have your pod with a sidecar, and then you have multiple auth methods. So as you saw in the Nginx example earlier, or Nginx config example, we were doing an include of a Lua script called auth.whatever. So you could have three of those scripts. One does Redis auth, one does an auth API call, another uses shared memory. And in the location blocks is where you define which one of those is called for which type of request. So we might deploy a sidecar that only ever sits on V1 and only ever uses shared memory. And the fact that the config exists in there for the other endpoints doesn't matter. It'll never trigger. It makes no difference. But we can deploy that same sidecar to V2 or to another API completely. And then these mechanisms begin to work. So it consolidates our authentication design into a single entity that's very easily manageable, easily scriptable, easily templatable. And we don't have to worry about it. You just deploy it as a sidecar, and it just goes. So in summary, our delivery pods are all self-contained. We don't have any authentication tiering. We don't have to worry about multiple moving parts in order to deliver authentication. This is very fast. We can handle very high traffic rates. We try to measure our rates in like a standard Kubernetes node. Running these should be able to handle multiple thousands of requests per second, depending on the configuration. And the higher you get, the more memory you have, the more pods you can run. You quickly wind up with I/O bottlenecks more than you wind up with processing bottlenecks for authentication anyway. It provides solid protection from spurious requests because they're eliminated before they even get to an endpoint. It's effectively infinite horizontal scalability. You don't have to worry about multiple tiers that have to be scaled along with it. For most cases, you can just keep adding pods, and the pods keep adding the auth, and if your endpoint that's in the pod alongside it is also very horizontally scalable, then you literally just keep adding pods to handle the load. It's easily managed and updated, as I mentioned. Timers can fire. You could trigger events to live systems. You don't have to go through and delete pods and have them restart to get updates. It's a configurable, effective deployment of changes. So when we do distribute changes, we can trigger them. We can, obviously, when we make a change to the configuration and we redeploy them, they get redeployed. But that's all handled through Helm and templating. Universal configuration, single pod definition can be used anywhere. We can support multiple auth mechanisms and backends. And if we needed, we could also do the standalone config that would handle all kinds of things: load balancing, TLS termination, or authentication. So it's not just in Kubernetes that this makes sense. This could be your API gateway as well. So with that, I will open it up to Q&A, and please tell me if you want to go back to any of those slides, and I can provide any more detail on anything. I'm happy to do so.
Thank you, Paul. That is indeed super interesting. Actually, we do have 2 questions in the chat pod. I will read it for you. One is for Javier. He's asking if the Lua JIT code crashes, what is actually happening to the Nginx worker and the request?
Ideally, the Lua code doesn't crash. We test it. We try to keep it simple. But if it does crash, the worker should exit. And if the worker exits and this becomes a crash loop, then the pod will stop answering the health checks, and Kubernetes will flag it as a problem, and that then becomes if there's a problem in the code, then we need to fix and redeploy. But we should have enough logging to take a look at that. So we rely on those. If it's 1 or 2 workers crash because they wind up with an issue, we hope that the logging is sufficient to pinpoint the problem, and we can start to debug. But if it's actually taking the pod down with it, then Kubernetes should let us know, and monitors should be going off, alarms should be going off, and we would start to investigate from there.
In addition to that, I will ask you one other question. If the worker dies, what happens with the request? You will lose the request, or you will process the request by another worker, with another worker, or redistribute?
I believe the request is lost in this case. If the worker exits abnormally, I think I think it throws a 502, and that would be the end of it. Maybe a 503. Depends on what happened.
And the client probably needs a retry.
Yes.
Okay. And there is another question on the chat pod from Alberto. Where can you customize the logging for the authentication workflow?
So there's a number of ways to do that. It depends on, obviously we use standard Nginx logging. We produce log files that go through Kubernetes. We use Stackdriver and feed them to various places. That's just the standard GCP tooling. So if you're looking at that level, if we can get the logs that we need through the normal process, then we do. And Nginx and OpenResty provide some substantial ways to customize your logging within the configuration. However, as I mentioned, there are ways that you can distribute logs from Lua itself, like through AMQP, through MQTT. You could use, I believe there are plugins for AWS services as well, where you can have events be distributed through a message queuing system that could be then logged at that level. So if you can't get what you need from logging directly out of Nginx itself, and you can produce logs directly out of the Lua code too, straight to the standard out in the pod or standard error. You could distribute them through a message queuing system, Kafka, whatever you wanted to do. I think there are Kafka. We don't use Kafka anymore, but I believe that there are Lua bindings for Kafka as well. So I hope that answers your question. If not, give me more detail.
Thank you. It seems that, yes, it answered the question. Any more questions from the audience? Now is the time. Well, it looks like we don't have any more questions. Thank you, Paul. Let's have a 30-second break and continue with the second talk.
All right. Well, thanks for having me. This is. I hope this was interesting. It was very interesting to come up with.
It was, and I really hope to find out more from you in the next editions. Maybe you can share some more technologies that you guys work with. That would be super interesting.
Happy to do it.
Hey, Xiaofan. Xiaofan is the second speaker we have. Are you ready to share?
Yeah. Let me share my screen.
Okay, you're on.
Can you see properly the slides?
Yes.
Cool.
We can. Gonna back off, and you're on the spotlight.
So should I start now or wait a bit more?
If you feel free to, yes, let's do it.
Yep. Okay. So, hi everyone. My name is Xiaofan. I'm from Booking.com. Today my talk is about scaling go-carbon, the go-graphite storage stack at Booking.com. So before I start the talk, I need to give you guys some context and some disclaimer. So even though my talk today is about the graphite stack, but I'm actually not from the graphite team from our company, and this is mostly a personal effort. Although I receive a lot of helps and from the graphite team, especially Alexi. And they are kindly and bravely deploying my stuff on production. Some of them, one of them gets good result, the other is still kind of stuck. And yeah, and it's this whole story is a vertical scaling story. So to begin with, some of us here probably already know what graphite is, but just to give other people some basic knowledge, graphite is a time series database. It was originally written in Python, and the whole tools consists a lot of components like the front-end Carbon API for returning time series data, or Graphite Web for rendering graph. And there's a relay component which is responsible for transferring data from the producer and to the consumer, the graphite storage stack, and then the storage part, and also some admin tools like bucket tools. Another part of the graphite, some graphite basics. A graphite query, typical graphite query looks like this. So it's basically a file path, but instead of divided by a slash, it's divided by a dot, and you have and then it kind of consists as a hierarchy and namespace for each matrix. And accompanying with each graphite matrix, you also have a retention policy and aggregation policy. It's so for example, the 1 second 2 day here is called an archive in graphite, and it will save secondary data for 2 days long, and for the second archive it will be 1 minute for 30 days, and for 1 hour 2 years. And whenever it was aggregating data from the first archive or from the second archive to the third or high archives, it's using average as an aggregation policy. And there's some interesting facts in the metric path of the aggregation policy is that usually the first archive accounts for the largest part of the final file size of that matrix. For in this example, it actually accounts for 74% of the whole matrix. for the first archive. And a typical graphite data point will look like this. It consists of a timestamp and 32-bit timestamp and a 64-bit value. This is a typical, not like typical, a common deployment for many other people. I found it from the Graphite website. But at Booking, the deployment is very different. Not only we have rewritten a lot of components, some of them more than once, and the scale is different. I think we have, last time I checked with the Graphite team, is 400 million metrics, unique metrics across the whole company. And in many of these rewrites, many of them are actually written by a Booking employee or ex-Booking employee. The Carbon API is the most notable one. We also have our own Booking fork. It's started by Damian, Grisky, and Vladimir. And then we have our own relay now. Before it was Carbon C relay, also ex-Booking employee now is relay written by our Graphite team using Go, called nanotube. And there's a Go Carbon storage layer. That's my story today mostly about. So a bit more context that I came upon our Graphite stack in a hackathon in 2018, and then later the year I learned about the Gorilla time series data compression algorithm, and it gave me a very deep impression. So then I started to figure out what kind of compression algorithm our Graphite stack is using, and then I noticed that it's not compressing data. So I think it's a good opportunity, and decided to give it a shot by introducing the algorithm to the system. So in the Go Carbon, the Graphite storage stack Go Carbon, each metric is saved in as a file using the round robin database format called Whisper. There are a few important properties about Whisper. One is data point adjustable, which means that given a random time spec and a target archive, like we were mentioning, like you are talking about the 1 second archive or the 1 minute archive event, and you could infer its location in that file. So this is a very critical property and makes it very easy to support out of all the data write and rewrite. And also another property is that each Whisper file has a fixed size. And this is kind of a simple illustration of what a Whisper file looks like. It consists of header and then multiple archives. And each archive is the time series data, directly and uncompressed. And about the Gorilla compression, it's a compression algorithm published by Facebook in VeroDB15. It has great compression performance for time series data, although it's payload dependent. So which means that for many time series data, it has very nice compression ratio, and for some data, it might not deliver good compression. But in practice, many people find it to be the most efficient time compression algorithm, and it has seen wide adoption since its publishing. M3DB Prometheus, to name a few. Some of these use a slightly different version of the algorithm. They add their own tweaks, or they introduce some new properties like M3DB. It actually has some support of Lucy compression, so which means that the data that you save is not exactly the data that is returned by M3DB, but it's optional. And the core of the Gorilla algorithm consists of two parts. One is delta encoding for the timestamps. It's actually delta of delta. And then the other part is using Zo for the floating values. So for time series, for delta, it's kind of might be easier to understand, is that for each timestamp, starting with n and then n-1, n-2 in this graph. And then instead of saving the whole 4 timestamp, which in graphite's case is 32 bits long, it actually saves just the delta of the timestamps So this means that you don't need the whole 32 bits or 64 bits size for saving the timestamp. And for raw value, when you are resolving between time series, so this one might need a little bit explanation, is that in time series database, you tend to have values that are changing between a specific range. And so maybe you have a low average matrix, and your solver is not receiving low or receiving constant low. It means that your value is fluctuating between a specific range. And because of these properties, if you resolve these values of one timestamp to another, you get a lot of 0 bits. So in this case, in the example case in the paper, is that in between 24 and 12, if you resolve this value, most of the values becomes 0, and then you only have a very short meaningful bit. So this means that you don't have to save 64 bits of data in the file. You only save the leading length and the meaningful bit length and the meaningful bits, both size and the block. And combining these two solutions, it delivers a very promising result. So in the paper case, it's saying that in the example is you only need 21 bytes instead of 128 or 96 bytes, depends on your timestamp size. And the best case example will be something like this. You have a timestamp, a secondary timestamp that keep increasing, and then it means your delta is always 0. And that means if you are using the Gorilla compression algorithm, you only need 1 bit to save to save in the file, and then you could decode it back to the 4 timestamp when rendering it. And same for value. If your value is always 0, then you only need 1 bit to save it in the file and then decode it back to 0. It doesn't have to be 0. It could be a constant value, and then you only need the result will be the same. But if your timestamp or value are random, which is the Gorilla algorithm not really good at with, you would end up with a bigger file size if your data is random. But in practice, most of the timestamp data is quite predictable. And now the problem is that I need to find a way to combine Gorilla and Whisper files. So this is the end result that I designed. You still have a header in the Whisper file, but you also need an archive index. And then in each archive, instead of directly saving data points, it's first divided as different blocks. You have block 1, block 2, and then in each block you save the time series data. The reason that we need to introduce block is still using the example that we have back then. If you have 1 second, 2 days in the first archive, if you are not using block, then all your data points is compressed continuously. So whenever you only want to retrieve the last 2 hours of data, you will have to decode from the beginning of the archive until the end of the archive, which might not be efficient because now you're spending a lot of time decoding, encoding, even though you only need part of the data from the archive. So that's the benefit of using blocks. So the end result is I named the new file format CWhisper, which stands for compressed whisper. It's kind of boring, but it conveys the meaning. And in this new file format, it's still a round-robin database, but it's no longer, the file size is no longer fixed. It has to grow or extend over time. That's the reason for this is that we don't know what kind of payload this metric is saving, so that we don't want to pre-allocate a bigger file if your metric ends up only needing a part of it, a small part of it, like the example that I was giving, the best case example. But some metrics might end up needing bigger file size. So the balance that I'm making is I have a default data point size, which is 2 bytes. So whenever you create a new metric, you will start with a 2 bytes per data point as the, and then whenever your file keeps, when you start writing data to the CWhisper file, if it detects that there's not enough space to keep all your data, it will grow. And like I said before, archives are split into many blocks. Ideally consists of 70 to 100 data points, which is recommended by the paper. And yeah, another loss in the new file format is that you can no longer address a single data point. So this also means that it's hard to support rewrite, and you can only have limited out of order range. It's most of these trade-offs are shared by almost all other time series database that also supports compression. And the end result was quite promising. You have when we were first testing in one of the graphite clusters on production, in that cluster we have around 50 million metrics, and for the standard Whisper file you have it has 32 servers, and the compressed Whisper file it has 9 servers, and all those servers have the same hardware profile, so that this space is the same, the CPU is the same, memory is the same, and the total disk usage that CWhisper cluster is using is 45% less. And there's some discrepancies of total metrics in these two clusters because some metrics are retired faster or in different clusters. So even though the majority of the metrics are the same, there's certain level of discrepancies, but it will usually smooth out over time. And the theoretical capacity per server for CWhisper is doubled compared to standard Whisper file. So when we first have this result, we were quite happy, but then we noticed another problem here is that the go-carbon that we are running actually has per instance actually has a magic count limit up to 5 million due to a query index that is unable to support it at that moment, and this means that even though we can support 10 plus million metrics in the same server, we cannot actually send all the metrics to that server if the query index is not improved. So naturally, I start working on improving the querying index. So a little bit about how a graphite query works is that it's super simple. It works like a graphing in a shell. The syntax is the same. This is a very simple example of retrieving metrics using this pattern. You have start with 6 CPU, low average at host 0, and then you have a start at the end. And if you do an LS as of the same path, you would expect the same result to return. So naturally, you want to, because all go-carbon is written in Golang, so naturally you want to use the file path match in Go standard library. The pro is simple to implement, but the problem is that the cost was too high when you are dealing with a large file tree, and if your queries are trying to looping over a large part of it. And the file path group is a user space implementation. So every time you want to loop match a path, you first need to ask the kernel to return all the files, and then you do the grouping over it. And so the actual query index that we are using in Go Carbon is using trigram, which is originally written by Damian Grisky. He's also one of the authors for Carbon API. And the way it works is that it breaks down all the metrics as trigram and then maps all the trigrams to that matrix, which is an inverted index. And then when a query comes in, it will also convert it as trigrams. And then you will intercept the two trigrams, and then you will have a list of files. And the list is not the end result. You will still need to use grep to make sure that the files match the query. So this is some kind of a nasty part of this implementation. And the good part about using trigram is that it's faster than standard library. There's no syscall after index, and file lists are cached in memory. But the problem is that the index is expensive to build when dealing with high numbers of metrics, and the result returned by the trigram index are always matching the query. That's what I mentioned before. And I'm skipping a lot of details for the trigram index because it's a pretty big topic itself. And my solution is to use try and NFA DFA. I learned about so NFA DFA stands for non-deterministic finite automata and deterministic finite automata. I learned about this from Golang author, one of the Golang author, Ross Coase, in his post explaining about building efficient regular expressions using NF and DFA. And this is a great match for the grabbing syntax. I think it's actually also used in the Golang standard library for file path grep and also the regular expression library. And the try index part is fairly easy to understand. You just index all the metrics in a try tree, prefix tree, and this is how a matrix looks like when it's indexed by try. And you could see that for 6 CPU low average app and host 000, there's only one copy of the strings in the whole try index. So this is very efficient when you are doing comparison, because comparison is only done once and it saved a lot of memory. Well, when trigram, when you are building an inverted index, you all need to keep the whole copies of every strings. It's not compressed. And then NFA this is an example of using an NFA representing the grabbing expression. This is the most simple case of it. So that you're starting with a prefix, and at the end you want to get the host 1001 and 2001. And the way it works that you would build this as an NFA automata, it's very easy to build. The cost is also quite low. And then when we are working over the try tree, it would dynamically convert the NFA to an DFA. We how do I say? If we pre-compile an NFA and DFA, the growth could be exponential. This for this simple example, it doesn't really have this issue. But if you are having some complex grabbing queries, it could lead to high memory usage. And the whole algorithm works like when a query comes in, you have we build an NFA, and then at the same time we start working both the try tree and the NFA. And at the same time, we feed the NFA with the try tree results, and then you would dynamically compare to an NFA, DFA. So the whole process is is like walking two trees. And this means that comparison is only done once, and it grows, and the cost grows as linearly as your metrics grow. So these are all the benefits that the new solution have, and it's super fast to build and try, comparing to build a trigram index. In my test, I think for trigram it would take like 1 minute, 2 minutes to build a whole index for metric trees with the size of 8 to 10 million. But for tri index, it's only 10-20 seconds. And you use much less memory. And you don't have to fall back to a standard library. Then it has better and predictable performance. There are some downsides of using tri and NFA DFA, which is some of the, if you have contained some very specific keywords in your matrix, it's actually faster to use trigram, because that's what trigram is good for. If you have a keywords, you have a way less, you have a much smaller set size to intersect with. The end result that we have is this is the query histograms of production queries against production metric file trees. And we see that tri and DFA have much less tail latencies comparing to trigrams. Yep, that's both sides of that's kind of my whole story for these two implementations. There's some tips that I was mentioning before, that if you are using tri plus an DFA index, it's better to have the most common namespaces in front to be in the beginning of your matrix, so that you have better memory usage and query latency. But unfortunately, so for rolling out to production, so two technologies actually are meeting two different destinies. For CWhisper, because of the out of order and rewrite support is limited in CWhisper. At Booking, we have an event pipeline that's generating a large number of metrics that many of our services are using. And the nature of the event pipeline is that it will produce the metrics, produce data for the same metrics in a distributed manner, which means that the producer won't be coming from a single host. So you could receive a timestamp now, and then later you could receive a timestamp that's 30 minutes late. And this is very hard to support in CWhisper format. And then sometimes you have outages in the event pipeline, and then you need to rewrite the matrix data. And both of these two requirements are nicely supported by the Whisper file format. So this kind of limited the potential of using compressed time series database at Booking. But however, the tri and DFA index solution made it to production, which ironically I spend way less time working on this technology than in compressed Whisper. But yeah. And to defend a little bit about the out of order and rewrite support is that it's not a problem specific to CWhisper. It's if you are using time series database that use compression, you would run into the same issues. So you have to make trade-offs for your system. You cannot eat your cake and have it too. And that's some of my the last part is about debugging and testing. Is working on this stuff. You need to, for working on a new file format, you want to able to analyze what kind of bytes you are writing, and then you need to have proper tooling for migration. So I implement a lot of like a few tools for doing this purpose, and it helps a lot for developing it. And then for the try index, you have unit tests for sure, but you still want to have to use production queries to verify if the new solution is returning the same results matching the old solutions. And fuzzing and randomized input is also a big help. The last bit would be, once again, make special thanks to Alexei, the best admin that I ever know, and our Graphite team for bravely testing and deploying these changes. And so throughout the talk, you could kind of tell that my way of working on this thing is figure out what kind of problem it is, and then applying a well-resourced algorithm onto an existing system. And both of them use very good results. So there's some anecdotes that I try to inventing my own tricks or improvements into the implementation, but I usually fail miserably. So I think it could be a good learning tip that it's better to look up some well-researched papers or algorithms to address that problem. It would save a lot of time, and you would have a really nice result. It was a great learning journey. That's kind of it for my whole talk.
Thank you, Xiaofan. Well, that's indeed interesting and quite a research project. We have a question for you from the audience. Javier is asking, there was a clear decrease in storage usage with the compression, but what's the increase in the CPU usage from the compression decompression? Triggered?
So before, when you are writing to a standard Whisper file format, it's you don't need to do any processing. You just write directly to the files of all the bytes that you receive. But with compression, you need to first decode some of the data from the file, and then you need to encode it. And then also in C Whisper is also calculating a CRC32, so to make sure that to detect data corruptions in a specific blocks or a specific archive, or in a specific Whisper file. And all this leads to higher CPU usage. But the good part is that in our observation, usually the Go Carbon in the server usually have like 12 CPUs, but for serving standard Whisper files, it only use like 2, 3, 4 CPUs. So it's there's a lot of wiggle rooms that you could in terms of CPU. So it's not really a problem. I/O per second was actually an issue because when there are way more metrics saving in a single box, and it needs to do a lot more I/O. So yeah, that's kind of it. Hope it explains. No
Okay,
problem.
You have a thank you there.
Yeah, in Chinese.
Any other question for Xiaofan from the audience? Okay, I think that's it for today's edition. Thank you both presenters, very interesting. I think we had one of the most technical editions so far. I will follow up with everyone from the Meetup platform with the recording on YouTube and along with the slides, the PDF files. and hope to see you soon with a new edition next month. Thanks, everyone.
Thank you.
Have a great day, evening, morning, wherever you are.
So.
Bye.